Welcome. This video is going to take a look at the three different octet rule exceptions. What I mean by that is that some molecules don't follow the octet rule or don't form a new compound or a new molecule with 8 electrons around each atom. And the reason for that is because there aren't enough electrons available. So what the atoms do is they use the electrons available to get as close to octets for all the atoms as possible. And so it's better than not bonding at all, but the molecule it forms is less stable and more reactive than the molecule would be if it did have the perfect octets. So the three common kinds of exceptions, or the three common situations where we'll form these imperfect molecules, are when we have an incomplete octet, an expanded octet, or an incomplete octet with an odd number of valence electrons. And I'm going to work lots of examples in this video and give you a chance to work some examples and see if we can make this a little more clear to you. So an incomplete octet forms when not every atom has 8 electrons around it. And now these are incomplete octets with an even number of electrons, and this only happens with two very small atoms, boron and beryllium. Remember, hydrogen and helium only have the one electron shell. The only 2 will do for that. And boron and beryllium also can get away with just 2 if they lose those electrons. And they are metals, so sometimes they lose those 2 or 3 valence shell electrons they have, and they just form an ionic bond. But they can also share their 2 or 3 valence electrons and form covalent bonds. And when they do that, it looks like you could draw double bonds and give them a full octet of 8, but the reality is it's way too crowded because the nuclei of your boron or your beryllium are going to be literally right on top of each other, and there's going to be too much repulsion. So only single bonds form, with boron bonding to, hydrogen or fluorine or whatever it's bonding to, or the same thing with beryllium bonding covalently to some other atom. So let's take a look at an example of this. So my example here says, draw the incomplete octet for BeCl2. Now, when you're asked to do these in class, I'll give you a hint that it's not a perfect octet. You don't have to recognize when these abnormalities or exceptions come up. So we know it's not going to form a complete octet. So if I follow my procedure here, I look up my total number of electrons. Beryllium has 2 valence shell electrons, and the 2 chlorine each have 7. So that gives me a total of 16 electrons. And so if I put Be in the center, and I bond a chlorine to each side of it, then it looks like I would put 2, 4, 6, 8, 10, 12, 14, 16 lone pairs around, but I've also got the 2 bonds. That means I've used 20 electrons to make this stable, so I've used 4 extra electrons. Now remember, normally that would tell us to go back and make double bonds, such as this, and then I just need 2 sets of lone pairs on each one, 2, 4, 6, 8, 10, 12, 14, 16. This looks like an ideal situation, but the reality is that these 2 chlorines would be so close to that beryllium nuclei, the chlorine nuclei and the beryllium nuclei are going to be so tightly packed together, it just isn't going to happen. So even though mathematically this looks like a good option, it doesn't happen. So what does happen? Well, what happens is beryllium just forms the single bond with each chlorine, and then the chlorines get their lone pairs, and then we just leave these 2 empty spots here. And that's why it's called an incomplete octet. Beryllium is stable with just the 2 bonds or the 4 electrons around it. So here's an example for you to try. Draw the incomplete octet for BH3. And remember, boron will not form double bonds to get a complete octet. It will just go with what it has. So I would encourage you to pause here and try this on your own. And I will go ahead and put up my solution. So I've got boron with 3 electrons, 3 valence shell electrons. I've got the 3 hydrogen, each with 1. So we're working with a total of 6 electrons here. And so if I put boron in the middle, attach each hydrogen, I see that boron only has 6 electrons around it, so it could use another lone pair, but I don't have any more electrons. I've used all 6. Hydrogen has no more electrons to share, and even if boron were able to make a double bond, hydrogen can't. So this is as stable as BH3 gets. The second exception is something called an expanded octet. Molecules that form with more than 8 electrons around the center atom have what's called an expanded octet, which makes sense, more than 8 in the octet. And this can only happen with a period 3 or bigger element. And the reason why, if you think about it, is because periods 1 and 2 only have s and then s and p orbitals, but when you get to period 3, now you have d orbitals. And if you're having an expanded octet, you need more than 4 orbitals to put electrons in. Because even though the octet can expand, each orbital won't hold more than 2 electrons. So the d orbital gets pulled in to hold the extra pair of electrons, and it can form for 2 ways. You can have more than 4 atoms bonded to the center atom, or you can have extra lone pair that are hanging around the center atom. In either case, you're going to end up with the center atom having more than 4 pairs or 8 total electrons. So again, we'll take a look at an example here. It says, draw the expanded octet for PCl5. So using my usual method, I look up phosphorus and see it has 5 electrons. I have 5 chlorine that each have 7 electrons, so we have a total of 40 electrons to place around this molecule. So I put phosphorus in the center. I attach the 5 chlorine. And now some of you are going, wait a minute, you can't attach 5 things. You only make 4 bonds around the center atom. But that's why this is going to be an expanded octet, because all 5 chlorine are going to attach. It's more stable to have all 5 chlorine attached like this than to do something like this. Okay, that is not as stable. It's more stable to be expanded. So that's what happens. It goes ahead and expands its octet because phosphorus is a period 3 element. And then each chlorine needs 3 lone pair around it. And then if you count up, I've got the 5 bonds. So 2, 4, 6, 8, 10. And then I've got 6 more electrons around each chlorine. So I have 10, then 16, 22, 28, 34, and 40 electrons. So I've used my 40 electrons, but to do it, I've had to put 10 electrons around the center atom, around phosphorus. So that's why this is considered an expanded octet. So here's an example for you to try. I've got SF6, and again, the hint is that you'll know it's an expanded octet when you place more than 4 atoms around the central atom, or you have an extra lone pair, which will have to get placed on the center atom. So go ahead and pause here and try this yourself. So for SF6, I have 6 electrons for the sulfur. I have 7 for each of the fluorine, so this is a total of 48 electrons. And similar to my example that I already worked, I see that sulfur is going to be my center atom, and that means 6 fluorines are going to be placed around this. So this is very much an expanded octet. I've got 12 electrons, 6 pair around the sulfur atom. And then each fluorine is still going to need its 3 lone pair. It's going to get kind of crowded here. So when I count up here, I've got 2, 4, 6, 8, 10, 12 around the center atom, and then I've got 6 more on each fluorine. So I've got 12, 18, 24, 30, 36, 42. I've got 48 total electrons with 12 electrons around the sulfur, making it an expanded octet. But this is still more stable than not bonding at all. Here's another example for you to try, XeF4. And go ahead and pause and try this. And when you start drawing this, when you look up Xe and you see it's a noble gas, right away it's like, really? I thought noble gases were stable. And they are, but under certain situations they can be made to react. So this is a reaction that's going to be endothermic. You're going to have to put energy in to make this happen. And there's reasons to do it. So I've got 8 electrons for the xenon. I've got 4 fluorines with 7 each. So 28 and 8 is a total of 36 electrons. So I put Xe in the center. I attach the 4 fluorine. And so far this looks good because I just have 8 electrons around the xenon. But now when I go ahead and put in my lone pair, I'm going to need 3 lone pairs, 6 electrons on each fluorine. And now when I count up my electrons, I've got 2, 4, 6, 8, or 4 pair around the xenon. And then I've got 6 on each fluorine, so I start with 8 plus 6 is 14. And then another 6 is 20. Another 6 is 26. Another 6 is 32. Now, this is an unusual situation because I've only used 32 electrons. So I've got 4 more electrons that need to go somewhere. Usually we've used more electrons than we have when we go form double bonds, but a double bond is going to make this worse. We've got too many electrons. So what happens is those extra electrons get placed in the d orbitals around our center atom. So xenon ends up with an expanded octet anyway because it has 4 bonding pair and it's got 2 lone pair. So it's got a total of 6 pair or 12 electrons. So this is also an expanded octet. The last exception to look at is an incomplete octet with an odd number of electrons. And this happens commonly with polyatomic ions forming that don't have a metal to pick up the extra electrons from that they need. So polyatomic ions are the most common you're going to see here. This is before they've picked up the -2 or the -1 charge because they haven't found that extra electron. So incomplete octets can form with elements other than boron and beryllium if there aren't enough electrons for the center atom, and it's going to end up with an odd number of valence electrons until those electrons become available, and like I said, probably from some metal. And a hint here that adding a double bond to get it to 9 doesn't make it more stable because 9 is more crowded. So less crowded is better. Plus, then when it finds that extra electron, it's not getting rid of electrons, it's simply going to pick up another electron. So if possible, it's the central atom that's the incomplete octet because it keeps the molecule more symmetrical. Just like it's the center atom with boron and beryllium that's incomplete, and it's the center atom that ends up expanded. So think about keeping it balanced. If there's imbalance, we put it right in the center of the atom. So let's look at an example here. I have NO2, and when I count my electrons, I have 5 for the nitrogen. I have 2 oxygen with 6 each, so I have 17 electrons. Now, as soon as you come up with an odd number of electrons for your total, then you're going to have an incomplete octet with an odd number because you can't get an even number of pairs. You can't get pairs of 2 from an odd number. I can get 8.5 pairs out of this. That's the best I can do. So I put nitrogen in. I bond on the 2 oxygen, and then I fill in the lone pairs I need. So each oxygen needs 3 lone pair, and the nitrogen also needs 2 lone pairs. So when I count up, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 20 electrons I used. So my difference is 3 electrons that I'm short, okay? So I can add 1 double bond, would get me closer, but 2 double bonds isn't going to help. So, because remember we divide by 2 and that tells us how many double bonds to make. It's telling us make 1.5. Well, I can't make half of one, but I can make 1, so I can improve this by putting a double bond with one of the oxygens, leave the others a single bond, and then this oxygen would still need 2 lone pair. My other oxygen would need 3 lone pair. And my nitrogen now has 2, 4, 6. It would like a lone pair. But now when I count up, I've used 2, 4, 6, 8, 10, 12, 14, 16. I've used 18 electrons, but I only have 17. So this is my hint that nitrogen is just going to have to go with 7 electrons and have an incomplete octet until another electron becomes available. So here's an example for you to try. This is similar to the one we just did. So pause and go ahead and try this. It shouldn't be too difficult. So I have 5 electrons plus the 6 for oxygen. I've got a total of 11 electrons. When I draw NO, I need 3 lone pair on both the nitrogen and oxygen. So I've used 2, 4, 6, 8, 10, 12, 14 electrons. And just like my example, I have 3 electrons left. So I can redraw this with a double bond and then put 2 lone pair on each one. And now I've used 2, 4, 6, 8, 10, 12, which is better, but I'm still going to need to take one of these electrons off of nitrogen, and nitrogen is going to be incomplete with just 7 electrons, and that's the best I can do. And again, that's better than forming a triple bond and putting 9 electrons around nitrogen. You won't see an expanded octet with an odd number. Here's another one that's going to come out a little bit differently for you, so go ahead and pause and try this one. So when you count up your electrons, you see chlorine has 7, 2 oxygen have 6 each. So I end up with 19 electrons. So again, I know right away I'm going to have an odd number of electrons or an incomplete octet. And if possible, the incomplete octet will be on chlorine. So I bond the 2 oxygen on with single bonds. I fill in the lone pair. And I count up. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. So that's just 1. So that would only be a half bond, so I can't go ahead and make a double bond. It's not going to help me. So instead, I just have to remove the 1 extra electron I had. And now this is an incomplete octet with chlorine having just 7 electrons, but the 2 oxygen being complete. And that's an introduction to exceptions to the octet rule.